This is the introduction to hypothesis testing, the content of the current module. And in this discussion, we're going to talk about the concept of the logical disjunction. We will return to this point shortly. We are talking about inferential statistics. As we transition from descriptive statistics, we talked briefly about probability. And the next stepping stone on this path is inferential statistics. This is where we take information about the sample and we try to infer information about the population. The first thing we talked about was estimation, which was accomplished via calculating confidence intervals. Now we will move to decision making. For this, we will use NHSTs, null hypothesis statistical tests. There are three key points we will address here in this introduction. The first part is the logical disjunction, which is what happens anytime you have evidence that can be used to support two competing and sometimes contradictory conclusions. There are at least two logical paths you can take to lead you to completely different conclusions. The next key idea is the analogy of the U.S. courtroom. If you go to trial, you are declared to be guilty or not guilty. And the key is that not guilty is not the same as innocent. While we might hope that one would be declared guilty or innocent, this is simply not how the U.S. judicial system works. What we will see is that this parallels the conclusions we can make using the NHSTs. Lastly, we will talk about the Strawman argument, which some might refer to as a proof by contradiction or reductio ad absurdum. Some might disagree with this characterization, but we will see there is an element of contradiction in the process of reaching a conclusion with the NHSTs. So this is setting the stage. But before we progress, we will take an aside to talk about empiricism and scientific reasoning. When people like to disingenuously make attacks against the nature of science, they always try to attack science based on what it can't do, instead of addressing what it does and claims to do, and what it does well. Now, there are certain things science can't do, but good scientists acknowledge this. They don't try to claim otherwise. That said, empiricism is just the idea that we will use evidence that we can find in nature or evidence that can be observed. That which can be observed is what is used as data in empirical science. Scientific reasoning imposes two restrictions on how we can use empirical data. The first part is that we can only disprove a theory, or a claim, or a proposition. For whatever we are focusing on, we can't prove anything. We can only disprove things. Second, we can only disprove a statement of equality. These are the only two rules we have with empirical reasoning. Again, I can only disprove a theory, so let's take a look at a scenario that helps exemplify this. The advantage is that sometimes by disproving one theory, I might end up proving another theory. But the key to remember is that all I can do is disprove. I can't directly do the proving part. The proving part may come along as a consequence, but it is not something I can do directly. Simply put, I can't prove to you that cows exist. But what I can do is disprove that cows don't exist. How do I do that? We walk up together to a cow, and I show you the cow. This is a cow. Therefore, I have disproven that cows do not exist. By consequence, I have proven that cows exist. But I did so by disproving that they do not exist. Now, the second rule is that I can only disprove a statement of equality. So, what was my statement of equality with the cow scenario? The way we represent the statement cows don't exist is written mathematically as the number of cows equals 0. So these two statements capture the same concept. To confirm, this was the statement I disproved, and it was indeed a statement of equality. Furthermore, I couldn't disprove the opposite statement, cows exist, because this would be represented as the number of cows is greater than 0, a mathematical statement that does not contain the condition of equality. Let's move from this silly hypothetical example about cows to something more authentic. My new goal is that I'd like to prove two variables are correlated. Unfortunately, what I can't do is prove that there is a correlation. Why? Because I can't prove anything. I can only disprove things. But I can disprove things. So if I want to show there is a correlation, I should disprove that there is not a correlation. Or I should disprove the variables are uncorrelated. This is not too bad because what does it mean if two variables aren't correlated? Well, I can write that out mathematically. R equals 0, which is clearly a statement of equality. If the correlation is 0, then the implication is that the variables are uncorrelated. Said another way, r equals 0 implies there is no correlation. If I can disprove this statement, r equals 0, then that implies r does not equal 0, or better yet, r equals some non-zero number. And if the correlation equals some non-zero number, then the variables are indeed correlated. And this foreshadows the structure of the null hypothesis tests that we will be working with shortly. Here's a situation I would like to reflect on with you for a bit, and it mirrors some of our earlier discussions. I have IQ data on 120 individuals. Recall, for the standard IQ instrument, the scores are centered at a mean of 100 with a standard deviation of 15. And you will note that the curve drawn here is not the population distribution, because it clearly does not have a standard deviation of 15. The standard deviation would be closer to a value of 1. Instead, this is the sampling distribution for samples of size n equals 120. Again, this is the distribution of means of size 120 you would expect to be randomly drawn from the population. From an earlier calculation, you may recall that the probability of obtaining an IQ score of 102 or greater is 44.7%. This is the probability of randomly selecting one individual and having their IQ score be 102 or greater. However, if we have a sample size of n equals 120, the probability of getting a mean greater than or equal to 102 is 7.2%. Again, this is a problem we've worked through previously. Using a conventional cutoff for what would be considered unusual, unless we have a cutoff of 10% or so, this probably wouldn't be small enough to suggest that a sample with a mean of this size or larger would be considered unusual. That is, 7.2% usually wouldn't be considered unusual. Now, here we have our actual sample. This sample has a mean IQ of 103.5. In this context, we can determine how often this might happen by chance. It turns out the probability of getting a sample of 120 individuals with a mean of 103.5 or larger is 0.53%, or roughly speaking, this is a chance occurrence of about 1 in 200. I'm hoping you recall how to get these percentages using the norm_dist function in Excel. And we can see from the shaded region that this is indeed a relatively small probability of happening by chance. To clarify, I could say that I believe this blue bell curve to represent reality, because I know it agrees with what I know about the sampling distribution for the conventional IQ test. And what I have is an observation of 120 individuals with a mean IQ of 103.5. Let's apply the same question as above. Would this be a surprising finding? Well, if we are using a cutoff of 5% or 2% or 1%, this probability is less than that alpha level or that arbitrary cutoff value we are using to classify an event as unusual or not. So either we observe something uncommon, something that happens only 1 out of 200 times, or something else is at play here. Now, I have a question for you to ponder, and this question is to get us to think about how we might adjust our perception of quote-unquote reality. Under most conditions, we would say that the probability of getting a mean of 103.5 or higher, which is 0.5% of the time, we would say this is an unusual occurrence. Well, that is true if the blue curve is an accurate representation of reality. So, is it possible for our version of reality to change? Well, what if I share with you one additional piece of information about this sample? This is a random sample, but it's not a random sample of adults, it's a random sample of students currently enrolled in a Calculus 1 class. What changes in your mind when you learn this additional piece of information? In particular, do you still think the blue curve is a correct description of reality? And if we are talking not about 120 randomly picked students or adults, but instead randomly picked students enrolled in Calculus 1? Said another way, would you be surprised to find 120 students that were enrolled in a calculus class had a mean IQ of 103.5 or higher? I think most students would tend to agree that it wouldn't be surprising. The rationale would be that because the sample is coming from a class studying mathematics, there's a better chance that the IQs will be higher than you might find in a random sample. Now, while there are issues with IQ tests that shouldn't be overlooked, this seems to align with our conventional understanding of how IQ tests work. Some might even argue that IQ tests are less about measuring intelligence and more about measuring things like abstract reasoning, which is a skill you might expect to be stronger in a sample of students from a calculus class. So while there are questions about what the IQ test might be measuring, most people probably wouldn't be surprised to find that the calculus students taking the IQ test perform, on average, higher than the general population. Thus, it seems reasonable that the orange curve might give a better representation of the IQ distributions for calculus students, and the distribution of means of samples drawn from calculus classes. So let's summarize this. The idea is that the orange curve is how we adjust our version of reality once we have the additional information about the students being from a calculus class. In other words, I no longer think the blue curve is an accurate representation of reality for this context, and the orange curve is probably better. This sets us up nicely to talk in more depth about the straw man argument. In truth, the scenario I just presented was simply to set the stage. This generally is not how we would go about an analysis with a null hypothesis statistical test. Generally, we believe the orange curve is true. Going back to the picture, the curve positioned further up the IQ scores is what I believe better captures reality, at least for Calc 1 students. But despite this, I am going to assume, at least temporarily, that the blue curve is true. To reiterate, I believe the orange curve is true, not the blue curve, but we will temporarily believe or assume the blue curve to be true. By doing this, my hope is to show that the calculus students have average IQs higher than the general population. This is the information about the general population, the blue curve. I'm going to temporarily believe this is true, even though I actually think the orange curve is a better representation of reality. Again, this is what we refer to as the straw man argument. Some might also call this proof by contradiction or proof via reductio ad absurdum. But the point here is that we are going to claim something we don't believe in hopes that by following a chain of logical events with our evidence, we obtain a contradiction of that initial assumption, that thing which we didn't actually believe in the first place. My hope is that you see how we are setting the stage to disprove something. Now, the reason why this is not a proof by contradiction is because we are using empirical evidence to obtain the contradiction instead of a chain of logical conclusions. The reason this is better classified as a straw man argument is because this argument relies on a logical disjunction. Simply put, the evidence that we are going to provide to support our claim can be interpreted in two different ways. Let's unpack this now. Our hope is to use unusual events as evidence to support our argument. The idea is that we hope to show that the probability of our event occurring is so small as to be practically impossible. We collect a sample, and from that sample we get a statistic, and we then have an observation, an empirical observation. More specifically, we hope to show that the probability of our event occurring under our assumption is so small, ideally so extremely small, as to be practically impossible. This is our hope for how we might use an unusual event as evidence. If it is so extremely unlikely to have happened by chance, if our assumption was true, yet it did indeed happen, then that means our initial assumption wasn't true. The problem is that there are actually two interpretations of finding an unusual event. So let's say we are successful. We collect our data, and we calculate the probability of our data happening by chance. It turns out to be a rather small probability, and thus it can be classified as an unusual occurrence. We are now left with two choices. First, our assumption is indeed true, and we actually did observe a rare occurrence. Surprise, surprise, unlikely things happen every day. They happen all the time. Now, yes, they may not happen in abundance, but that doesn't mean they never happen. You may not win the lottery every day, but this doesn't mean that someone doesn't win the lottery somewhere. That's the first scenario. Something rare happens. The second scenario is that there was something wrong with our initial assumption. Unfortunately, finding a small probability is supporting evidence for both of these two scenarios. And the first scenario suggests our assumption was true, or at least doesn't contradict it. And the second scenario suggests our assumption was incorrect, and that is the logical disjunction. We have one piece of evidence, the sample we collected, and it ended up leading us to two very different conclusions. Let's talk now about the cycle of the straw man reasoning. To address the issue or flaw associated with the logical disjunction, We are going to apply a rather weak band-aid to a relatively large problem. However, this may be the best solution we can hope for given the constraints of this form of logical reasoning. What we will do is pick an arbitrary cutoff. Then, if we obtain a probability for our result that is below this cutoff value, then we will consciously choose to accept the second conclusion. Again, there are limitations with this approach, but this is how the null hypothesis testing works. This is not to say it is a fatal flaw in our reasoning, but it is a concern that must sit in the periphery, if not persistently at the forefront, of our attention all the time when doing NHSTs. So here's the strawman cycle of reasoning. The starting point is that we believe A is true. A is some statement or research claim. Next, we will assume that B isn't true instead, and B is the exact opposite of A. That is an important aspect of our analysis. This form of logical reasoning holds only if A and B are mutually exclusive and exhaustive scenarios. It is either one or the other and nothing else. More on this shortly. Next, we want to locate evidence that contradicts this assumption, that is, contradicts the statement B. If we can locate such evidence, we can then conclude that B was wrong. Again, we believe A is true, and this leads us directly to setting up our straw man, our temporary belief in B, the exact opposite of A. Again, we don't believe B because it is the exact opposite of A, but we will pretend that it is true for the time being. Our goal is to now find evidence that contradicts B, because if B is indeed wrong, then we have strong evidence supporting my original claim that A was true. To clarify, if B is false, and if A is the opposite of B, then A is true. Let's walk this through with a quick example. If our claim, statement A, is that two variables are correlated, then the opposite claim would be that the variables are uncorrelated, statement B. If we obtain a sample with a correlation bigger than the critical value, then we have found evidence that contradicts the claim that the variables are uncorrelated. And if the variables are not uncorrelated, then this means the variables are correlated. We will revisit this example again shortly to add mathematical notation to it. If any of you have had any debate training or competed on a debate team, you may have encountered this idea of the strawman argument. In that context, more often than not, if you try to use the strawman argument, you set yourself up with a number of potential issues and problems for your argument. Let's take a look at an example of a strawman argument that is used rather ineffectively to justify a claim often heard by some political pundits and current politicians. Note, I am critiquing the effectiveness of the logical argumentation. I can't speak to the emotional or affective effectiveness, as that is a different aspect of the speaker's ability to sway people to their beliefs. Let's say that I am in favor of extremely limiting access to the country in which I live, and consequently, I want there to be very little immigration. To convince others, I might suggest that if we don't severely limit the number of incoming immigrants, then we are going to let in tons of murderers and rapists. Do we want more murderers and rapists in our country? No, of course not. So the quote-unquote logical conclusion, logical here is in very exaggerated air quotes, is that we must indeed have a strict immigration policy. This is an example of a straw man argument, where in this case, the straw man that was propped up for the purpose of being knocked down was the idea of having a lax or weak immigration policy. Well, I'm hoping you see the major flaw in this logical reasoning. Simply put, the suggestion that there will be an increase in the number of murders and rapes because of more immigrants is not justified. It draws on fear and prejudice and exaggeration, not on empirical evidence. In fact, not only is there evidence to suggest that this group of people is no more violent than the general population, there may be compelling evidence to suggest that those immigrants in the country may commit crimes at a lower rate than the general citizenry. And this is how the straw man argument falls apart. As you pull at the threads of the logical argument, you see the cycle begins to unravel. Again, this is not to say anything about the emotional element involved in an argument like this, and that is a topic for other academic disciplines. And this generally is the reason you don't want to use the strawman argument when you are engaged in debate. So doesn't it seem strange that I have been presenting the strawman argument as something we should do in statistics, if it is not something we should actually be doing when we talk with people or engage in argument or debate? Well, yes, except there is a case when the strawman argument is okay, and that is when the criteria in the first step is met. that is, when B is indeed the opposite of A, and when these two scenarios are the only two scenarios that might happen. Quick aside, one might argue that the cycle for the immigration argument meets this criteria, and the flaw in that argument is the logical reasoning that more immigrants means lots more criminals. However, I would suggest that this criteria is implicitly unmet in that the opposite of letting no one in is not letting in only criminals. These two scenarios may be opposite, but they are not mutually exclusive, as you could let in only non-criminals or let in a cohort that might include both. So let's see why the strawman argument works in the statistical framework, even if it doesn't work in the rhetological framework, like the immigration example I just proposed. The strawman argument works in the null hypothesis statistical test. Remember, NHST stands for null hypothesis statistical testing. Let's revisit an earlier scenario. We claim that two variables are correlated. This symbol is rho. This is the Greek letter rho, R-H-O, which corresponds to the Latin letter R. It looks like a P with a slightly longer and curved tail. In the way we use the Latin R for the correlation of a sample, we use the Greek rho for the correlation of a population. If we claim two variables are correlated, this is equivalent to claiming that the correlation of the population is not zero. We will call this statement A. So what is the opposite of A? We will call B the opposite of A, and in this case, B would be that rho equals 0. Now, why does the NHST work as a strawman argument? Well, we've met the two main criteria. First, these are indeed opposites of each other, and there is no other possibility for what rho might be. These two statements are mutually exclusive, i.e. opposites of each other, and exhaustive, i.e. there is nothing else it can be. Now, let's start to introduce the terminology and notation for the null hypothesis test. Our statement B here is what is called the null hypothesis, and we label this as H sub naught or H sub 0. Thus, the name of our test, the null hypothesis statistical test. Whereas our original claim was represented as statement A. This is called the alternative hypothesis, and we usually denote this as H sub A or H sub 1. I just want to reiterate that the NHST is a bit of a backwards approach. Let me show you what I mean by that. Generally, we believe that HA is true. The consequence of this is that the null hypothesis, H sub 0, the opposite of HA, this second hypothesis becomes the strawman, and we move forward assuming H0 to be true, but we do not actually believe that the null hypothesis is true under most circumstances. Here's the end of class question for this content. If the null hypothesis that we are currently working with is H sub 0, is unicorns do not exist, then what is the alternative hypothesis? And this can be expressed in words.